Professor Ximing to start? Okay, let's go ahead and have you start, Professor Ximing. Thank you so much for joining us. And I'll be on mute and I'll let you introduce your topic. Thank you so much.
Okay, so I should start, right? Hello?
Yes, go ahead.
Oh, okay, all right. Okay, hello everyone. I'm Ximing Kai. Thank you for joining this presentation. And also thanks Columbia Water Center and Quasi for hosting this talk. I'm actually sitting in a hotel room in Beijing, and the time here is 12, is midnight. But don't worry, I already got enough coffee. I think I will gotta wait till the next 1 hour. So drought is certainly a very pressing issue for present Americans' water, and it is of course also an issue for the water issues for in the future. So we have some historical drought occurred in recent years, but also we have currently we still have California drought ongoing, and there are mounting evidence of more drought damage in the near future, which might come as a surprise and go far beyond our contemporary experience. So the question is, are we prepared for another major drought? To answer this question, we have to consider about a lot of issues. Such drought and climate, has climate intensified the risk of drought, and also the drought and forecast. Is there reliable forecasting information for us to use? And drought and the infrastructure, and so the question is current infrastructure and its operation underprepared or overprepared? And so for drought decision making and implementation, we have to consider about the institution situation and also the stakeholders' behavior. The question is, does the current institution support drought preparedness? Finally, for drought, we have to consider about both the social, both the natural and the social aspects. So to discuss those questions, I organized
Guests have been muted.
I organized my talk as this 4 parts. The first part, I will talk about drought features from a systems perspective. And then following that will be problems of drought preparedness, and then challenges in implementation. And finally, I will highlight integrated analysis framework for drought analysis. So drought should be described from multiple aspects, including the intensity, severity, duration. So given the correlation between this feature, this aspect, we will consider about the inter-arrival time or the return period. We usually have to consider about the combined multiple aspects of drought. And drought is also a behavior of a complex system. So it's related to hydrology, which decides Looks like I got some problem here. All right. So,
Professor Kai, hold on one second. I just want to see if people can. It seems like some people aren't able to hear, but also, are you able to control your presentation?
I just lost the control. I got it back now.
Okay. Let me know if you would like me to through.
Okay. Okay. Can we continue? Continue
Uh,
now? No.
okay, I see it's fine there. Great.
Oh, okay. Okay. Good. All right. So drought is also a behavior of a complex system. So as shown in this figure, it will be determined by hydrology for water availability, and also the actual water supply, and that depends on the engineering infrastructure, and then the demand or water requirement. So now we are talking about the impact of climate change on drought. For the but we all know we are facing some uncertainty. So there are many studies about the global trend of drought and climate change, but in the literature there are some conflicting results. So the IPCC assessment report 4 AR4 that report says the drought have become longer and more intense. But then, in AR5, it says, oops, something wrong with the. So AR5 says the IPCC report AR was probably overestimated about the drought happened before and also the drought in the future. And we also have some studies about the other recent publications about the drought trend for the future, and their results are not consistent. All right. So, but at the local or regional scale, we certainly we could do some more detailed assessment. So now in the following, I'm going to show you some results about the trend and some abrupt shift of certain drought indicators in this six slides. All right. So what we say in this slide is the duration of some drought events occurring in 100 years from 1900 to 2012. So we see the results from this 6 sites. We can look at some. So we can look at. Let's look at the Northern California. We can see some increase trends and then decrease trends, and then increase trends again in recent years. And in Southern California, we see one consistent increase trend of the duration. In Colorado, we see some extreme variability. The same for Texas. So in Illinois, as we can see here, there is a shift. So this is like a downward shift. And after the downward shift, we see an increase rate. increasing trend in recent years. In Maine, we see a consistent decline. All right. So now here in this slide, we can say the severity, how the severity changes over time, and the severity and the same. We can also say some increase or decrease trend or variability. So here we see the intensity, how intensity, the trend of intensity in different places. Okay, so now to assess the return period of some giant drought variables, we define some mowing windows of with a length of 40 years, and so this mowing windows moves the windows moves year by year. Now with this mowing, we can look at so here in we can compare go back here. All right, so looks like some symbols that's not symbols don't show on this. So basically here we look at the so we compare two sites. One is Southern California, and the other one is Illinois. Actually, in this one, let me look at it. So I think in this one we look at the duration and the duration and the severity in this figure, and we compare two cases on this side on the left side. So on the left figure we compare the case of both intensity, both duration and severity. And this on the right hand side we compare the case of severity or density. So the reason for us to use this bivariate return period. So first we want to consider about how like a drought with a short with a short duration to another drought case with a long duration, and these figures also show the shift and the trend. Okay, and then this one is the same thing. We show another two cases. We show the four types of drought with different intensity and duration. All right, so let's just go back to the drought features. So we often define different types of drought. So the meteorological, agriculture, and hydrological drought. So we can say that so from meteorological drought to agriculture to hydrological drought, we say the duration increases, and also the emphasis on along this direction, the emphasis on the drought event is declining. All right. So in terms of the 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 the, the context of natural and social drought, I think there some cases could give us some sense about the social impact. So right now we are facing the drought in California. Um, so um, the population is about 14 million. But in 1970s, the state of California had also had a severe drought, but over that time the population was only 20 million. Another case is the 2012 Midwest drought. In 1995, there was also a very a massive drought, but in that year, 55% of corn was used for domestic feed grain. But more recently, in 2012, more than 40% of the grain of the corn was used for domestic ethanol use. So this different uses of the crop might affect people's perception about the drought and finally the behavior of people's behavior. All right. So now in the following, I just show you an example to say how the impact propagation might behave like in a nonlinear way. So in this figure, we compare the number of different droughts. SPI represents meteorological, and SSWI is for agriculture. SRI is for hydrologic. So we compare two types of drought. The upper one is the intensity less than -1 and the duration is equal to 1. And the lower figure shows with duration equal to 2. Um, and the results are from two emission scenarios. So if we compare the number of different droughts, we can say actually you can say that they are increased from or in other words, the number of droughts from different aspects, they are not identical. All right. So since I talked many things about the drought feature, I hope I could use this slide to summarize a little bit. So basically, I want to highlight the 4 points. First, the drought is a complex behavior depending on hydroclimatic engineering and socio-economic factors. And when we talk about drought, we usually face a risk with multiple correlated aspects, including density, severity, and intensity. So when we look at what happened in the past, we could say a series of trend, shift, and extreme variability. And those situations are collected and also and the last point is about the impact propagation, and so here I want to highlight the nonlinear propagation from meteor to socioeconomic. Right. Now I move to the next part. So given in the context in a system context, given all these features, let's look at how what kind of decision problems we have for drought preparedness. Okay, so facing the drought in California today, the California state governor, um, and he said, now it is a different world, and we have to act differently. So now we know the recent ordered 25% cut of water use, and even more, the water use, the water right holders, they have been warned they might have to their water use might be restricted, and also the federal government has also responded to the current drought event, and they provide emergency loans, and they are working with the state to speed up investments. So some federal agencies also link the information with drought preparedness in critical sectors to manage drought-related risks. So the keyword here I want to highlight is keywords here. I want to highlight include investments for some capital investments for infrastructure, and the other one is risk management versus the traditional crisis management for drought. Okay, so currently the desalination is seriously considered in California. So for example, in Santa Barbara, they plan to build a desalination plant, but it's quite expensive. The capital cost is about 40 million. The operational cost is as high as 5 million. So you can say from this slide there are some interesting statements about interesting discussion about the desalination plant, and so people try to um, try to think about if we need to do something different rather than take a kind of tactical measure for crisis management, and they are thinking about if they need a risk management measure. So that means if they need to do something even when drought not happen. I think this statement is interesting. It just shows people are really thinking about, are really put risk management into a very serious contest. So although the decision for drought management sounds to be difficult, but this picture actually shows a bold decision. And we know in desert, this is always have probably the very extreme drought. But we can say here there is a 10-mile long golf field. So you can imagine the decision here is related to the people's demand and the financial support, and probably also some some political factors. All right, so we can probably support the decision the decision problem into this framework. And so the question here is, if we want to do something now, so if we do something, if we say yes, and then if in the future, if we have more serious drought, and then our decision would be right, then we have some appropriate adaptations. And if drought just happen, if future drought just happen as a historic drought, then we'll end with over-prepared situation. And so this is what the traditional engineering planning has tried to avoid in terms of cost minimization. And another case is if we don't do anything now, and then we also face two situations. If more serious drought happens, and then we might end with an under-preparedness situation. And I think probably in many places, and this might be the situation. All right, so now it looks like from engineering perspective, investment perspective, the major issue here is if our investment or our infrastructure is over prepared or under prepared, and the complexity here is actually the forecast by the uncertainty of the future. Okay, so people called this kind of decision as a decision problem because the two issues. One is emerging risk. So that basically means the risk, or some people call that as deep uncertainty, because we usually could not use the traditional probability to describe the uncertainty. The other one is related to the trade-off. So when we make a decision, and that end with some trade-off between different aspects, or even between now and the future, and between human and nature, for example. Okay, so now in the following, I just use an example from my own group to show an example of decision making for drought preparedness. And the case study is in Republican River Basin. So we try to, the focus of this decision problem is to address the measures for now or for the future. And we define a three-stage here. That is the current decision, the midterm adjustment, and also the long-term decisions. And so we consider about multiple objectives, infrastructure investment. We try to minimize that, and also we want some environmental benefits from environmental perspective. And of course, so since this is a very important agriculture basin, agricultural profit is important. Looks like there's a, I don't know what happened. There's a problem with the slides here. Okay, so let me just talk about this slide. So basically here in this figure we say under different discount rate, from 2% to 6%, and what is the fraction of the investment for the current stage, which is shown by the below color, and what is the fraction for the second stage, that is the red color. And so in general, we can say, based on our results, we found the fraction for the current investment is higher. But with larger discount rate, and the ratio for current decision for the current investment declines a little bit. So in general, we found early investment has a larger fraction than the later investment. And the other thing is a higher discount rate. And so here we use a true interest rate to represent that. And that leads to a larger fraction of infrastructure development and a larger fraction of later investment, and also an improved trade-off relationship between irrigation and investment. So we can say that from the right the right figure. The right figure here shows the trade-off between low flow in the river and the crop yield, and we can say that so with higher discount rate, the trade-off is improved. Okay, so this is the example about the decision-making problem for drought preparedness, considering the future uncertainty and the climate uncertainty, and also the future uncertainty of socio-economic conditions. So the next topic is next item is about the challenges. I'm going to talk about some challenges in implementation. So here I will cover two aspects. One is about the role of institutions for drought preparedness. So here I have a very so following an existing presentation, I have a very brief summary about the institutional development for drought preparedness in the U.S. Before 1980s, the state relied on assistance from federal governments, but after that, we see a rapid increase in drought response plan. So currently there are already 38 states. 38 states they already have such a plan, and in recent years we see more emphasis in those response plans. More emphasis is given on mitigation planning based on risk management. So at the national level, we also see some risk-based national policies developed by federal government. So we can say, such as the National Drought Preparedness Act, and on the technical side, we have the National Integrated Drought Information Systems. So in general, we say, starting from 1980s, we see some development of institutions for drought preparedness with emphasis on risk management. Okay, so to have some discussion about the role of institutions, so here I discuss a little bit about the 2012 drought. So there's no doubt the 2012 drought is a historic one, is a great one, given its impact. But the question here from a news report is why did it not it go social? And so I believe many of you, I believe we still remember that drought, but it looks like people are even during that period is the response from the society is not as strong as as we have for California drought today. There are some related the nature of the drought. So that's probably because it does not really last that long compared to the California drought. But there are also some, factors, such as the government agriculture policy. I'm going to talk more about that in later slides, and also is related to the general belief and the perceptions about the food supply situations. And the people usually people don't believe the food supply situation might be affected by that very serious drought event. Okay. News report which even shows some more interesting statements. It talks about some secret side of the drought, and it basically says although some farmers during that drought event some farmers they got lost, but others they even got some benefits. So has caused the concerns of stakeholders. So basically, in the event, some farmers their income, if not increased, but at least it does not decline much. That's because the crop insurance, and in some cases they got a subsidy from the government, and another reason is mainly the market, because in later season the price of corn went quite high, and that some way compensates the farmers' loss. Okay. All right. So let's move back to the current case of California drought in terms of the institution, and so regarding how to deal with the current drought and the future even more serious drought in California, and some people are thinking about to learn from Israel, because the water situation in Israel is even more limited than California. But Israel is well, so why cannot California learn from Israel? But from some scholars show some concerns about that learning. So, for example, Professor Cohen of UCLA, his major point is Israel is related to the institutional status of California and Israel. So basically, Israel has a unified water policy, and the price is national consistent. But in California, the water prices vary from location to location, and only Los Angeles have over about 100 different water suppliers. Other thing is Israel has a national policy to accelerate desalination. But in California, desalination has been discussed for a while between the environmental concerns and the water supply security. And given these situations, it may not be that easy for California to follow exactly what Israel has done. Okay, and also on the institute, there are some measures, like for example the 25% cut And actually, we know the cut is not cut ratio is not even. It's from 4% to 60%, and so the wealthy communities are facing higher cut. But there are also some news report. They say actually the price penalty does not really impact the wealthy communities very much. The real impact is about the communities with relatively low income. For farmers, the state water board has requested farmers farmers with junior water rights to stop using the river's water, the water from the river. So that happened about 1 month ago, but so far only a fifth of the junior water holders in the region have followed that order. On the other hand, some farmers they even start to pump more groundwater. So in basically this, so when we consider about some institutional changes during this drought event, we also see some economic divide in the region associated with the drought. So for the implementation, another important fact from a technical perspective is the role of the forecast information. So in general, we have short-term, middle-term, or seasonal, and also the long-term forecast or predictions. And we could use different type of use the forecast with different forecast horizons for different purpose. So for 2012 drought, there are some research reports. They indicate the difficulty of predict the forecast of that drought event. So for the scientific community, a critical question is if whether or not a forecast model can capture the drought or can capture that drought may can that be so that may translate into improvements in predictions for the future. So for Midwest, many Midwest regions with rainfed agriculture, the seasonal forecast is especially important because once they put the plant in the field, they will not be able to do much. It's not like irrigated agriculture; they could still do something. When they could irrigate to mitigate the drought impact. So the decision issues for rainfed agriculture could include the land use and the crop pattern. So for example, in central Illinois, if farmers know some information about that drought in the beginning of the season, so they might choose to plant soybean or plant corn. And that might also affect the use of fertilizer and also the marketing. So actually, in central Illinois, so the farmers who were hurt most seriously are the so-called contract farmers, and those farmers they made a contract with ethanol plants in the beginning of the season or even further before. So they got a fixed price from the refinery plants, But in that year, unfortunately, because of the drought, they just could not they could not produce that produce the amount as they promised, and then later on they had to buy corn using a higher price from the market. So those farmers, they even some of them they have insurance, but because they could not uh, um, keep the contract promise, they got some higher loss. And of course, the insurance also help on affect decisions. So now in the following, I just show some analysis in terms of different forecasts and also the impact of the possible impact of different forecasts on farmers' income and also farmers' decisions. So in this figure, in this figure we say so we have two types of, one is the real forecast. It's the forecast based on the climate weather research model, and the other one is the reanalysis. The reanalysis basically is kind of revised. It's a kind of handcast. It's modified forecast based on the post observation, and we have so here we show the different forecast in the critical crop growth period from June, July to August. And so those start points represents the observation. So basically here we can say that the forecast scenarios tend to overestimate the precipitation in crucial months of June and July. And so we can also say the reanalysis improves the forecast significantly.
Like we've lost audio. Can you hear me?
I just got it back. I'm sorry about that.
Oh, that's
I
okay.
think there might be an internet problem. I just got it back. Okay,
Okay.
let me so let me just continue. Sorry. So here we just compare the forecast in terms of the observation, and correspondingly we can say based on different forecasts we could estimate crop yield, and for corn obviously we can say if we use the forecast, the real forecast, then we will overestimate the crop yield very much. But if the forecast is as good as the reanalysis, then the crop yield is quite much close to the observation. So on the other hand, I mean that also shows how good the reanalysis is. Unfortunately, I mean if the nature forecast could be as good as the reanalysis, then that might be very useful. All right, so now in this table, we just compare the net benefit, ex post net benefit, net benefit, the benefit on based on the post observations, and we also show the value, and this value basically means the value of forecast. It means the difference between what farmers could have obtained by using information and the farmers' actual net benefit after the crop season. So what we can say here is if we use this, if farmers really use the save-off forecast, and their profit could be worse off. So that's one point. And the other one is the optimal decisions with the reanalysis forecast are much wiser because we can say that the profit of farmers is quite close to the case with perfect forecast, and the value of forecast is also close to that value under perfect forecast. All right. And also we see the impact of impact of insurance as an example of institutions. So here we compare the value of forecast under 3 insurance plans. Revenue protection is the strongest one, and yield protection is the middle one, and the other case is without insurance. Okay, so based on the numbers here, we could find as the scales of forecast becomes higher, becomes higher, the stronger insurance may reduce farmers' profit. So actually we can compare the number here. So here this is 600, and then the long insurance, but under the strong insurance plan, the is only about 500 under perfect forecast situation. And on the other hand, as crop insurance gets stronger, the score forecast is less important. So that means if the insurance is really good, then the forecast farmers may not pay much attention on the use of the forecast. So the use of the forecast actually is the issue. The two basic questions is why are forecasts still not used effectively in agriculture and water resources decision making, and what should be done to increase uptake of the forecast information. So here there are basically 3 major factors. One is the forecast information, the uncertainty and the information delivery, and the other one really relates to is about the behavior of the users. So actually a lot of educational programs could help on this part. And the third part is the impact of the institution, as we just showed from that example. So finally, just sorry, I'm a little just delayed. Just a few slides about the kind of summary of what I just talked about. So here I say we suggested an integrated framework for drought preparedness analysis. So basically here I just try to combine what I talked about in this consistent figure. So we can on the top we have the drought characteristics, and also some both the natural part and the socio-economic part, and they were and that were the uncertainty from both parts will affect the risk assessment, and the risk assessment makes the decision and the implementation complex. But also, on the other hand, with the forecast information or monitoring information would help on the decision and implementation, and the behavior change and also institution infrastructure development will also help on implementation. So the last slide, I just show you some more questions in this consistent framework. So does climate forecast projection provide useful information? how will climate change affect policy and behavior or adaptation? And what happens if drought is unpredictable? And will socioeconomic drivers be a major source of vulnerability? How to make forecast actually used? And finally, does institution or infrastructure support decisions? Does institution or infrastructure support decisions and implementations? Last question is, does something we do something now, or we keep the ball down the road? Thank you very much.
Thank you very much, Professor Kai. I think we have maybe 5 minutes for some questions. Do we have any questions from the from people who are listening? If you have a question, you can type it into the chat. Okay, so we have a question from Michelle, Professor Kai, asking if you could explain further how an increased discount rate results in decision makers implementing irrigation investments sooner rather than later.
Okay.
Do you have any?
Yeah. Okay. So we may not have, because it's not easy for me to go back to that slides. Let me just. So first of all, for probably for details, so she might just go to the paper we recently published in Journal of Water Resource Planning and Management. So the basic idea here is we use that the discount rate is actually on the other hand, that reflects the kind of true interest rate. And so with a higher rate, basically means the future the economic situation would be improved. In other words, we have a better economic situation in the future. So under that conditions, we may not need to invest that much for today. We could probably wait and say for the future, or in other words, we have more flexibility to wait and say for the future.
Okay, so it looks like Manu has a question about if you have thought about the implications of long-term climate variability and timescales of persistent wet-dry periods of decades or longer in basins that are nearly fully appropriated, how would such a switching mechanism best be handled?
Sorry, I'm not sure I got the question. So the question is about the trend in the future, or the kind of decision with a longer future. Sorry, Marcus, can you some way repeat the question again?
Sure. You know what? It looks like Manu's typing a clarification here. I don't know if you can see his. Can you see the chat window?
Let me say, it's not that clear. Let me say.
Okay.
No,
Well, he
I
says
can't say.
you
Okay,
can't see
I
the
can't
chat
say.
window from your window.
No, I can't.
Okay, so he said he added the nature of climate leads to cycles that can last 10 years or longer in wet or dry. Yeah, does that clarify things? Long-term climate variability.
Okay, let me try to look at that. Oh, okay. Yeah, okay. All right. I think the nature of climate needs to cycles that last 10 years or longer in wet. Oh, sorry. What I say here, the question is not that complete. I'm sorry. The
Oh,
question
that's
is
okay.
This is the nature of climate leads to cycles that can last 10 years or longer in wet or dry. Oh, so actually we do find some when we look at the drought events in the past 100 years, we do see some drought events with a very long duration in the past. In the past 100 years.
Okay, well, I think that we're just about out of time, so thank you very much, and we appreciate it.
Thank you very much. Thank you, everyone.